Hello everyone and welcome to this virtual dynamic webinar. Please allow me to introduce first myself. My name is Ali and I'm the training manager within FEV STS. I've joined FEV 1 year now and I'm in charge as well of coordinating several webinars on several projects. Before we start, I just want to make sure that everybody can hear me well. So I will please ask you to use the hand icon that should be visible on the tool buttons that special for the webinar. So please click the hand icon. Perfect. There is some people that still can't hear me, I guess. Okay, very good. Now that we did the testing, I would like to give hand to Swapnil Shah. He's the application engineer that has been working since 18 now on Virtual Dynamic, and he will be the one providing you with the demonstration today. So I will pass on to Swapnil.
Great. Thank you for your introduction, Ali, and good morning, good afternoon, good evening to everyone who managed to join us today from all around the world. Yeah, I'm glad that you could make it today for the webinar, and I certainly hope that you are keeping healthy and safe in this slightly uncertain time. So welcome to the first of the two webinar series. Over here, we aim to familiarize you to working with Virtual Dynamics, the different tools and the different tricks which we have. So the theme of the webinar is I love VD. And I hope to bring something to the table for everyone, someone who is relatively new to the software and as well as the experienced users. And in the end, I hope that everyone goes back with after learning something. So Virtual Dynamics, it's Powertrain and Driveline Dynamics in your hands. Yeah, and we will be focusing over this webinar series, we will be focusing over creating a P2 hybrid topology. And today we will be particularly interested in the gear train and the electric motor. So the webinar will contain a lot of different topics. It will have we will talk about some basic tools. We'll talk about it's all about database, no troubles. Yeah, we will talk about the gear train, electric motors, and not only will we be talking about this modules in details, but we will also be looking at the higher details in the forms of roller bearings, maybe customizing some details. And then, of course, in the next webinar, we will be focusing more even on the crank train. And of course, we will create an assembly. So we'll put our crank train, gear train, and electric motor all together, along with test rigs and dynos, and create a P2 assembly. And we will also be looking at one of my favorite tools, which is enhanced animation control. So let me just switch to the session. And the first thing I will do is I will change the background color so that all of you are able to see my screen better. And let us actually start with looking at the different types of modes which are available in Virtual Dynamics. So we have the template builder mode, the standard interface mode where you can adjust and simulate, or you even have this Adams view mode where all the functionalities of Adams view are at your fingertips. And I will switch back to the template builder mode where we generally begin the construction of our models. So in the template builder mode, first let us have a look at the database. It's a very basic but a very important topic. What I'm going to do is in a particular folder, I am going to create a database for today's session, today's webinar session. So everything I do, everything model which we may create, we will do it over here. So I will name it webinar underscore database, and let's just create. So as you can see, the database was created quite easily. And you can link many different databases. If I go to this database info, I'll be able to see that, for example, I have 7 different databases connected to my virtual dynamics session, and some of them are default write. One of them is default writable with the double stars. So I would definitely want to change my default writable database to the database which we just created over here. So webinar underscore database. And what is, so I'm focusing so much on databases, and what is exactly a database? So I have a couple of slides. A database is basically an organizer. It helps to create a clutter-free environment, especially when you're working on multiple projects together. All the components, property files will belong to a particular database. And there is no correct answer of how you should organize your database. A database can be for a particular project. In a particular project, it can be for every variant or every loop. It can also be a universal database which links many different projects together, or it can link many different users who are working on the same engine. You can also link all of them in the same database together. Good. Let us now start with the first step of creating our P2 assembly, which would be creating a gear train. And I will open a gear train wizard for that, which is a very intuitive software which guides you in the correct methodology of creating a gear train. So I have 2 shafts as I just created, and each shaft will have a definite number of bearings and gears which you can define. So now I define the bearings, I'm able to see them and manipulate them as per my desire. I can select the position of the bearings. In the gears, I can even select much more information. Let me change the position of the bearing 2 over here. And what is important to understand, so now you see there is already a lot of default information for the gears here. I'll change the position. What is important to understand is that this gear train wizard, it creates a framework. It creates the basic framework for complex gear trains, but you can always change the fidelity. So let us do the same procedure for shaft 2, for example. So I'll have 2 bearings and 1 gear. I will change the positions. I will also change the position of the gear so that it matches with the shaft 1 gear. And it basically generates my entire framework. But in the end, let's build it over here. And what I have is a basic framework, and I will be able to create or change the model. I will be able to use different modules or higher fidelities for gears and shafts. We'll look all of that. Okay, so this is what we just created in a couple of minutes. And as you can see, my gears are really crashing into each other. It's because I have not defined a connection between the gear. Because in virtual dynamics, the gear element and the gear contact are always gear force between the 2 gears are treated as 2 separate components. So I can create a contact between the shaft 1 gear 1 and shaft 2 gear 1. And of course, the gears are positioned correctly on the shaft as we see, but there is no connection between them. So with this intuitive drop-down menu, it will not let you create connections between objects which do not really exist near each other. So for example, between shaft 1 and the shaft gear on the shaft, I can create a fixed joint. I could have even selected a constant bearing or another bearing. Similarly, I will do the same step for the shaft 2. I will attach the gear to the shaft 2 using a fixed joint, which I can, of course, in future change the fidelity. I can have a torsion spring or any different component. And let's build this new gear pair. So I have my entire functioning system with 2 shafts, 4 bearings, and 2 gears, and the contact and all the joints in the background are already created automatically by giving in some basic information. Like everything in virtual dynamics, this is also property file based, which means whenever I put in some work, I can very easily save it as a property file. Let's call it like over here. And this is where the database comes into the picture. This is the database which we just, for example, created. It's of course almost empty right now, but if I go to the wizard, this is the wizard file which I just created. And there it is. I have my wizard file, which can be also manually edited in the text editor, even right here, I have the two shafts, all the information on the positions of the gears and the bearings. I also have another wizard file open over here. So this is an existing wizard file from the shared database. It's much more complex for a 5-speed manual transmission. And again, this is a benefit of the database that I can access this wizard file, which we just saw, from any other existing database. So I do not always have to start from zero, but I import an existing property file from another database, which is very similar to what I maybe want to create today. So as you can see, I have my property file with the 6 shafts. All the shafts have relevant bearings and gears. And of course, all the information was already available in that property file. So let's just build this manual transmission. So this is one of the ways of creating your gear train using the wizard and manually creating the file. Another option is the Rex S option, which is going to come in the next release in a couple of weeks, hopefully, in some weeks, hopefully, where you can export your Rex's file from any compatible software and import it in the gear train wizard. And you can create such manual transmission, such complex gear trains really fast with such Rex's files too. So I will just save this. If you remember, this property file belonged to another database, so I just saved it in my current database so that in the future, after 2 months, I do not lose this information. And let me also just build the dynos. I don't really need them right now, but it's just easier to create the dynos already. And there we have it. As long as you have some basic boundary conditions and the information, you can build such a gear train. So let's talk about fidelity. Let me change the shaft, for example. One of the things which default is the shaft. I want a shaft with a much higher number of shaft sections. And I also want, let's say, shaft sections with different diameters. I can also have tapers. All the shaft sections can have different lengths, for example. And we can also already preemptively make attach markers on the shaft in case I know that in future I would like to attach some mass element or gear or a bearing at a particular position. So even though I use the gear train wizard, I can in the future change the fidelity and the complexity of any component. And that's how I have a much more complex shaft. And this is something which I can do for all the components. So I did not create the bevel gears with the gear train wizard, even though possible. And I will do it manually because I just wanted to show you an example of a manual creation of gears. And for that, you need a construction frame. So I'm creating a construction frame. I will attach it to the shaft 6, which is the output of my transmission. And I will also similarly make I want to make a bevel pair, gear pair. So I will also make a construction frame for the bevel 2, which I will have this dependency on the bevel 1. So all I will have to do is I will have this dependency on the bevel gear 1, right? And then all I have to do is change it by rotate it by 90 degrees. So I click on V as a shortcut so that I can see these icons. You can already see one of the construction frame for bevel 1 which we created. And let's create the construction frame for bevel 2. So what is a construction frame? It's basically a location on the ground which provides me the building block to build my entire model. It provides me with the original location and the orientation on which I can build up my entire model. So now that I have the construction frame, I can go and build the bevel gear elements. So let's create the bevel gear 1 over here. And I will attach it to the shaft number 6, the output from my manual transmission. And of course, we just created the construction frame for bevel 1, which I will also select over here. Rather than putting in all this information in this webinar, I'm just going to import one of the existing property files. Okay, this needs to be updated, and I will select a fixed joint. I want to fix my gear to the shaft number 6. And yes, so there we have it. This is one gear. Similarly, we can also create the second bevel gear of the bevel gear pair. I will select a different property file for the second bevel gear, of course. And in this case, I will just attach it to the ground. You could have also attached it to the housing if you want. I will select the construction frame, which we had created for this gear. And of course, yeah, it's on the ground, so it has to be a revolute joint. It can't be fixed on the ground, so we change it to revolute. And let's create it. So this is how manual creation of gears work. It's quite a lot of effort when you compare it to the gear trade wizard, which makes the life easier. And there it is. So I have my bevel gear pair also created over here. If I now I have the gear pair, but now if you remember, I still need to define the contact, because the gear contact and the gear elements are two separate entities. So I will just create a bevel gear contact. I will select the two bevel gears which I have, and I will leave all the parameters as default for the time being. And this is it. This is how I finally created a functional gear pair. If I look at the construction frames, so there are the two construction frames of bevel which we created manually. And you see Gear Train Wizard did a lot of work and created 20 construction frames. I also want to just change this dyno, which is connected to the shaft 6, to a more appropriate position. And in this case, I will attach it to the second bevel gear. And I will also, of course, select the J marker accordingly. So it will be this construction frame that should work. And this is how I can change the connection of any dyno. So this was all about the bevel gears and the Gear Train Wizard. And we talked about the different fidelity models. So what about the roller bearings? So in this case, let us select one of the roller bearings. I will change from default to the radial ball bearing. And I need, thanks to our flexible catalogs, for example, with filters, I will just give in the dimensions, like for example, in this case, let's say width and the inner diameter. And from the catalogs, I will be able to select a bearing. The groove diameters, the roller elements, the roller diameter, all of them will be estimated correctly by Virtual Dynamics in this case, which is great. Many users might know that such information of roller elements and their dimensions are not available from catalogs. Let's do the same thing with a different bearing, but this time we will change the fidelity. Instead of the analytical roller bearings, for example, I want to choose the geometrical roller bearing. So I will replace the analytical default roller bearing. The dialog box looks similar, but of course it requires a lot more information. So again, it will be the same process. Let me change to the radial ball bearing. And from the catalog, I give in the dimensions in the diameter, the width based on my shaft, of course, and I will select a bearing. All the other parameters get estimated automatically by Virtual Dynamics, or maybe read from the catalog, depending on what information is available. And this is how I can create a geometrical roller bearing, and I can change or play around with the fidelity of my model. So that's a geometrical roller bearing with 7 rolling elements, the way we just created right now. So this is the model, and let me go back to construction frame. So last time we created a construction frame with hard-coded values, like connecting it to a frame. So for that, I will create this two input communicators. So first input communicator, let's say this is, I want to do it for my e-motor. So I'm creating an input communicator for the LOC, the location of my electric motor, which I will be connecting with the gear train of the shaft burn. As an initial value, let's say I just give it a 000 and create an input communicator. Similarly, I need to also do for the orientation of this electric motor, which I plan to create. And so the entity type will become orientation. Let's just keep 000 as the start value. Now that I have my input communicators in phase, I can create a new construction frame, which will become the building point for my electric motor. So let's call it e-motor reference. And instead of hard-coded positions, I will just use the input communicators that we just created as referencing for my construction frame. So it becomes, it can also become parameterized. And that's now me, I have the construction frame, and now I can focus on starting and building my electric motor, for which I can use this global data wizard. In that case, let's just give it a name, P2 underscore e-motor. We will select the construction frame which we just created specifically for this purpose. And after that, of course, you need the basic boundary conditions, the basic dimensions of your electric motor. So I'm just putting in all the dimensions, stator length. Yeah, I get 186.9. Okay, so this is just basic dimensions which you should have. And what this will do is it will create the framework of all the necessary markers and the construction frames in the background. Again, let me see. Let me show you the markers. I think it was difficult to see. It was in the back of the model, but the markers just got generated for my electric motor. And then I can just go to the electric motor wizard like this and create the number of mounts. And it will generate all the components that will create a default electric motor for me, taking into account all the parameters, all the dimensions that we just gave. Okay, so here I have my electric motor. It's a little large for this transmission maybe, but this is the example which I had available. But as you can see, it is definitely not placed correctly. And this is where this procedure of working with communicators comes helpful. Let me show you the tree view, not through this menu. If I go to the tree view and I go to the input communicators, I can just select any element I want. And in this input communicator, let me give in this wonderful value, 259.5277. It's a very wonderful value, and I will actually show you how I derived this value from my own model to position my electric motor correctly. Similarly, I need to rotate my electric motor by 90 degrees, and there we have it. Yes, so now my electric motor is positioned correctly besides the second bevel gear as I wanted it to. So how did I get such a wonderful value to put in? And for that, I would like to actually go to the database navigator. Database navigator is the tool where all the information of your model is situated. It's very flexible. So for example, I can do topology by parts, in which case I can select any part and it will show me all the connections and all the connecting parts for the particular part which I have selected. Similarly, I have graphical topology. That's actually one of my favorite tools because it helps me visualize. It helps me visualize how the connection between the different parts is taking place. So over here, for example, I can see a gear is connected to the shaft using a fixed joint, for example. And similarly, talking about connections, so I have topology by connections, where if I select any connection, let me find the example here. So over here, I can see that the bevel gear is connected to the ground using a revolute joint, as we had just created. I go back to browse, which is, let's say, the general information about everything. And I will go to the bevel gear 2 at the gear part and the attach marker for this bevel gear 2. And over here, you are able to see this beautiful value 39.52777 something and minus 680. So I took this value, I added the length of my electric rotor, 220, and that's how I got the value of 259. So now my electric motor is positioned correctly. You know how I did it, but we actually also need to create a joint because it's not really fixed to the gear till now. And that's also something pretty simple. So I will connect it to the rotor from my e-motor, and on the other side, I will connect it to the gear part of the bevel gear 2 with a fixed joint over here. Yes. And we can use the construction frame from the attach marker. That should be appropriate. And that's it. So finally, I have my transmission for my P2 topology, a very primitive P2 topology, and you can see this fixed joint which you just created. Another way of creating this fixed joint is by shifting to the Adams view. As you can see, the entire virtual dynamics model has been transferred here. I can use any functionality in Adams view, create a joint over here, maybe a force element over here, or a spring, and whatever changes I make over here, I can do that. And once I shift back to virtual dynamics, all the changes will be incorporated in my virtual dynamics model. So this is also a great tool for many people to use. Maybe someone is more used to working with the Adams environment. Okay, so I'm just going to, oh yes, welcome to the new virtual dynamics help. It's much cleaner, much more agile. And what I'm trying to do over here is I'm going to open a tutorial because I also wanted to show you how these tutorials you can use to learn virtual dynamics. So I am going to use this tutorial. Let me place this side by side. I'm going to use this tutorial, which is basically gives me step-by-step instruction of how to replace my current rigid electric motor generator element with flexible components. So I'm just following the steps. For example, here in this tutorial, I will replace the stator with a rigid stator with a flexible component. And for that, the mounts will have to be, mount in my rigid stator will have to be updated so that they match the mount positions in my MNF, which I have already generated in this case. So that's why I'm changing the position of all the mounts over here. And once I have all the values, so I can change, I can update the mount position. And if we go to the next step in the tutorial, so now that the preparation has been done, I can set up a flexible electric motor stator. I can over here. So I will select the rigid stator which I want to replace in case you have more than one in your model, for example. Let us just create a property file with the name flex_stator, and I will basically select an MNS file. It's available from the shared engine database. There are a lot of examples. I'll just use the search function. And that's it. If the MNS has been already generated correctly, located positioned correctly, you do not really need to change anything. And I think I can just replace. Yeah, I'm sorry. I think there's something wrong with the system. Okay, also let me just try to give in the orientation as it has been already provided in the help, and replace the rigid stator with the flexible stator. It should take just, okay, so my graphical interface is not upgrading. Wait. Okay, so the replacement was successful. Now it updates my graphical interface. Yeah, there are sometimes benefits to home office, but sometimes the connections can scare you. Good. So as you can see, I have a flexible stator over here already. And the next step, as you can see in the tutorial, would be to have a flexible rotor. So again, I will set up a flexible rotor. I'll replace basically the rigid rotor which is existing right now with the MNF which I have already generated. I can't give in a name. I have to select the rigid rotor over there, and over here I can give in the name of my property file. Let's select the prepared MNF over here, and there we have it. So I replace it. I of course look at the message box which I will get. So let's replace it, and in the message box I should be able to see that the interface nodes were detected correctly. So yes, and that, and as simple as that, I have my flexible electric motor. I can now of course change the fidelity of my electromagnetic forces. So if if I go to electric motor and I modify the electromagnetic forces which the wizard had already created, there are different options of how detailed you want the forces to be. It can be a very simple torque element acting between two components, or you can have very detailed torque and force distribution where every tooth will have its individual axial and radial forces. As you can see in the tutorial, you can define many node sets. So if there are many teeth which are undergoing same forces, then you can just define a phase offset, and it's quite flexible and intuitive and fast. If you have a motor with 60 teeth, then you can define it here easily. I will not go and put in so many values during the webinar, and that's it. So you can check out the tutorial yourself. There are a lot of explanations, but this is it. I have my 5-speed manual transmission with an electric motor already coupled correctly. And now that I have reached this stage, what I want to do is I would like to save this template. I think I should have done it more often, but I forgot. So I should save my template before anything happens with the server connections in this on this day. And now that I have my template, so I can very easily switch to the standard interface and create a subsystem from it. So this step from going from a template to a subsystem is honestly a very child's play. My favorite convention is I always just prefix my template name with SUB in the beginning, so I always know which template is being used. We will select this template which we just created, and I do not need to change anything else. If I just click on OK, then it will create my subsystem. And it will be, of course, the exact same thing as my template. So this distinction between the subsystem and the template, it's very minor, but it's very important. I'll shift to a small graphic over here. So there are different working environments and your virtual dynamics model. Any model contains a lot of parts, constraints, forces, user-defined elements, the UDEs, which will all come together to create a template, which you will transfer to a subsystem and subsequently an assembly file. Right? And this distinction, if I look at this entire structure, maybe let us look at it in a little different organization. Then how it helps me is that with same template, I can create different subsystems. I can use a template as a base, and then many subsystems, I can connect them together to generate one assembly. So this way, I can change something in my subsystem right now, and it will not be reverse affecting my template, but I can always go and change a template, and I can change 2 or 3 subsystems together, which are all dependent on it, for example. So we did talk about the different fidelity levels, and on final fidelity level I want to look at today is, of course, the gears. So let me just open one of the gears, and the first thing which I'm doing, I want to show you how easy it is to generate a CAD geometry, an external geometry from the existing gear. So right now I have gears with internal geometry. I'm just making sure my working directory is correct. And all I have to do is click on export, and this internal geometry will get exported along with all the microgeometries and all the features that we have defined. You can also control the discretization of the gear geometry by selecting the number of points which you would want on your geometry in the CAD file on the tooth flank or on the profile count. So generally it takes a few seconds and should be done soon. And once I have it, I have already a CAD file. I do not have to rely on any CAD software or a constructor in my company to generate the gear geometry for me. I can really create many geometries easily. Okay, finally, I was getting a little tense over there, maybe server problems from home again, but not the case. So we can do the same procedure. So for one gear pair, I will select the gear on the shaft 2, and all we will do is click on editable and export the geometry again. You can also define an oil film thickness, but we will look at this oil film thickness and its effects a little more in a little more detail in the next webinar. And that's it. So I am exporting the geometry for my second gear pair in this case. The second gear of this gear pair in this case. It's taking a little bit longer than it generally does today, but that's how the world works, right? When you are showing it to 50 people, that's when it always takes a little bit longer. Great. So I have already exported my CAD files, right? And what I can do is I can now shift from internal to external geometry. I just need to set it up. So I will just, in the gear, I will just import this CAD file, this parasolid file which I had exported. It's intelligent. I do not really have to take care of the location from or the orientation. It's already been taken care of by the software. And that's it. So now we can just import this external geometry, and we have now increased the fidelity level of our gear train. Instead of internal geometry, we are using external CAD files. If I rotate it, the CAD file is actually nothing but an extension of or exporting of the internal file. So visually, it's not very easy to see, but there are these yellow segments which always exist on internal geometries. Let us do the same procedure and set up the external geometry for this gear. And you should be able to see that the yellow segment on the internal geometry will disappear. And that's how I know that my external geometry has been correctly imported. You can, of course, increase the fidelity level by converting these external geometries to flexible components. You already have the CAD model, and all you have to do is generate the MNF from there. And there I have it. I have one gear pair. Basically, maybe there is one gear pair that I really want to focus on, and I have increased the fidelity level of this gear pair in my model. So there are a lot of different gear elements and gear forces available in virtual dynamics. And let us now also change the gear force. So gear element, three-phase gear force, the default gear force which we had, to, let's say, the state of the art, the most complex gear force available to us, which is the general gear contact. This will, of course, require a lot more definition of the gear contacts, the oil fin, the stiffness, the force exponents. Luckily, we have this estimated and calculated options available. Impact is all what we are always using. I will leave all the other parameters as default right now, and just go to an overview of the different types of gear forces which are available in virtual dynamics. So basically, you can divide them into 2D gear forces and the 3D gear forces, and all of them have different fidelities and different strengths. It's, of course, the 2D gears require the least amount of computational effort, whereas the 3D gear approach will comparatively require a little more effort. But of course, then if you want to do a detailed analysis of gear winding, you want to do analysis, consider the oil fins, or you want to do the analysis of different microgeometries and its effect on the NVH, for example, then you would want to use this high fidelity model. There is also such a table available in the Virtual Dynamics help, which shows all the different types of gear forces and the gear elements and their compatibility. So what is compatible, what is acceptable, and what combination would actually might give you erroneous results. So you can see the 2D gear is compatible with, it's perfect with internal geometry. The 3D gear would work perfectly with external geometry or flexible geometry. It is important to understand this combination and always find the perfect combination which is suited for your investigation. And let's go back to the model. I see how much time we have, and I think I can show you one more feature. So I'm just opening a new Virtual Dynamics session. And what I will do is I will open an assembly from the shared engine database. There are a lot of options available. I'm opening a component assembly. What the feature I'm trying to show you is how to create the spline forces, the spline property file for the gear forces using Virtual Dynamics. I know many users, some users are still using this quasi-static software to generate the splines. But with Virtual Dynamics, so you can create 3D splines. It's very simple. So I have this assembly which Virtual Dynamics provided me. And what I'm going to do is I will change the property file. So I had a property file in my webinar_database, and I will just import it over here and replace this gear. And basically, the plan is to change the properties of both these gears so that I have the gear pair of my desire, which I want to investigate. So let's just do the same steps for the first gear. I will import the property file from our database and just replace it over here. You remember creating this external geometries and property files was quite simple. And over here, all you have to do is open this assembly and just replace the gear property files. And you have the gear pair over here, which you want to investigate. And now I can just do this component analysis for gear mesh stiffness. And it's divided into 3 parts. So submit analysis, export results. Submit analysis is obvious. Exporting results exports it to a property file directly, which also saves you a lot of effort. let us do the submit analysis, and this is how it looks like. The analysis dialog box, you basically have to say how many angles you want to rotate. I have selected the analysis type of displacement, so the backlash is for me important because I am generating a 3D spline which will be taking into consideration the transmission error in the gear pair. So the delta angle offset and the start angle offset will generate a range of transmission errors for which I will be conducting my analysis and creating my 3D spline. I don't think we have enough time to run this entire analysis today, but what I will do is I will go back to the help. So as you can see, you can do this evaluation of mesh stiffness for rigid as well as flexible gears, and a step-by-step instruction has been provided in the tutorial, and in the end you should be able to have a 3D spline which is dependent on the transmission error or the torque, which sometimes which is not taken into consideration. And this brings us back to the webinar highlights. I think it was fast and furious. We did cover a lot of different topics from the webinar today. And the next time we will be definitely focusing more on the crank train and creating the hybrid topology. And we will also look at the enhanced animation control tool. I hope you enjoyed this webinar and you join us again next week. And I am ready to answer any questions that you might have. Ali, I hand back the controls to you.
Yes, thank you, Swapnil, for this presentation and demonstration. So, if any one of you has a question, you can add your question in the question section, and we'll answer your question accordingly. In the meantime, I guess Swapnil, we can share the two question polls.
Yes, definitely.
So the first question is, which feature of Virtual Dynamic do you use the most? Please select one: a crank train, gear train, or other. So please select your answer.
Okay, that is quite a healthy distribution. So I think a lot of people will be interested in the crank train for the next webinar. Hopefully be able to show them some new tricks.
Yeah, still there's some people who didn't answer, so wait a bit. Please select your choice. We have almost everyone. Okay. The next question is, how was the speed of the webinar? So please let us know. Okay, thank you for your responses. So we have between perfect and fast, so I think maybe we need to slow down a bit next time. Okay, should we take questions?
Yeah,
Swapnil?
I just wanted to, I become greedy. I just wanted to show. Yes, please. Yeah, can you hear me?
Yes.
Yes, I am ready for any questions that you might have.
Okay, so we'll start by the first question. So has Visual Dynamics 2020 already released?
Yes, so you might have noticed that I was actually using Virtual Dynamics 2020 for today's webinar. It has officially not been released. What I was using was a beta version today. Right now, I am happy to say that till now our work as a Virtual Dynamics team, everything is on schedule. There have not been any delays, and as usual, we will be bringing you the new release of Virtual Dynamics 2020 near the end of April. But
Okay.
I was just using beta version today.
Okay. Hope this answer your questions. The second one is, does the general contact gear need external geometry?
I do not know how to answer the question because the answer is yes and no. Till Virtual Dynamics 2019.2, our latest release, you needed an external geometry to use this general gear contact, the highest fidelity. But that is something which we have worked on. And in the upcoming release, or in the next few weeks, the general contact gear will be able to work with internal geometries. We have also done, of course, internal comparisons and investigations, and it looks quite promising, which means you should be able to use this highest fidelity model without even having a CAD data file. Even though it's quite simple, but you would not have to go through this entire process. I hope this answers the question.
Yes, thank you, Swapnil. The final question is, how did you calculate the contact stiffness of the gear?
So I believe the question is related to the general contact gear, and the answer is twofold. So in the general contact gear, first of all, you have two different methods of how you use the stiffness and the damping. One is the calculated method. In this calculated method, the geometry of the gear, the material of the gear is taken into account, and the software calculates the stiffness of the gear contact for you. So it takes into account the microgeometries. It takes into account where the contact between the two gear teeth is happening. Is it on the pitch circle? Is it near the tip, or is it near the base? Because that also significantly changes the contact force, the contact stiffness between the two gears. But in the calculated option, you do not really have to select the stiffness. So this question would be more related to when I select the user option. In this user option, so it means that you want to calculate using a constant stiffness, which may be beneficial in some cases. And in this case, either you get the values yourself, otherwise Virtual Dynamics also provides an estimation tool. So this estimation is being done based on empirical formulas, which are derived from ISO standards, and also it is based on our expertise. So the stiffness, either you need to know it by yourself, or you need to calculate using an FE software, or the best option available to you would be to use this estimate button, which is the stiffness provided by Virtual Dynamics. I think this sufficiently answers the question.
Okay, and we just have another question now. Someone is asking, how are excitation forces in electric motor computed? Is electromagnetic model included in Virtual Dynamics, or does it come from another tool?
So the electromagnetic model is not included currently in virtual dynamics. So the electromagnetic forces do always have to come from, currently always have to come from some external tool. What we have done is we know that there are 2 or 3 tools out there, like Maxwell, for example, which are the most famous. And what we have done is we have created a tool which helps you import the forces and the torques and place them correctly on every single teeth individually. And as far as if I look at the excitation forces, so teeth, every tooth in my electric motor will have the axial force and the radial force acting on it throughout a cycle as a spline. And of course, that is how the excitation forces in my flexible body will be generated. I think I hope this is clear. If not, then please you can ask further question to this topic again.
Okay. Yeah, I think it's clear. Okay, so I have no more question for you, Swapnil. Do you want to add anything before we wrap up?
Nothing particular, but I hope to see all of you next week. And if you have any questions, please never hesitate to contact us. Thank you for your time.
Thank you everyone for joining. Do not forget that we have a next session on the 7th, next Tuesday, same time. So please join us as well. And thank you for attending again. See you next time. Thank you.